So in this session, we're gonna start with recursion, which is our next topic. One of those concepts that sounds intimidating at first, but once it clicks, it completely changes the way you think about problem solving. So let's start with simple question: what is recursion? So recursion is when a method solves a problem by breaking it into smaller versions of the problem. So in plain English, it's when a method calls itself to handle part of the work until it reaches a point where it can stop. So think of recursion as teaching your method to say, I can't finish this whole thing right now, but I can solve a smaller chunk and ask a smaller version of myself to handle the rest. So it's like divide and conquer, which is literally. Now every recursion method has two essential parts, and I want you to remember these words because they are the foundation for everything you'll be working on. So first is the number one is the base case. So that's the stopping point. So it's the point where the method says, have reached something simple enough, I can return without calling myself again. If you forget this, your method will keep calling itself forever. So, and you'll get a Stack Overflow error. And number two is progress toward base case. So this means that every time you make a recursive call, you move closer to that stopping point. If you're counting down, your number should shrink. If you're walking a list, your index should move forward. So without progress, a recursion never ends. It just keeps spinning deeper down the call stack until it crashes. Now let's talk about model, which is call stack. This is where your computer keeps track of which method is currently running. So every time a method is called, Java creates a little stack frame, a box that stores its parameters, local variables, and the place to return to. So when that method finishes, the box gets popped off the stack. The program goes back to where it left off. So when recursion happens, these stack frames stack up like a tower, one for each call, and then unwind as the results return. That's why understanding the flow of calls and returns is so important. When you debug recursive programs, you are not just running one method, you're running a chain of them that's constantly growing and shrinking. So when should you actually use recursion? You don't always need it. Loops can handle a lot of problems, but recursions always shine when your problem naturally contains smaller copies of itself. Think about these examples like, for example, searching through folders and subfolders on your computer, or another example could be working with trees or linked structures, generating permutations, exploring all combinations, or dividing a task into smaller halves like a binary search. So those are the situations where recursion feels natural because the problem repeats itself on smaller and smaller scales. And sometimes recursion just makes code cleaner than loops, even if it's not more efficient. For example, reversing a string, summing numbers in an array, or traversing a nested structure. So those are some examples. So once you see the pattern, base case, recursive case, and progression, it becomes second nature. An example is, imagine a simple method called count down n. So if n is 3, it prints 3. then calls itself with 2, then 1, and finally 0. So when n hits 0, that's the base case. So it prints go and stops. The key idea here is each call does one small piece, hands off the rest to the next call. So that's recursion in action, basically. Each step trusting the next one to finish the job. So yeah, we go through recursive methods, binary search, backtracking. I want you to focus on spotting these two things. First one is where the base case, the stopping condition, and how does the method make progress towards the base case. So if you can answer those two questions for any recursive function, you already understand 90% of recursion. So yeah, it's just smaller problems calling smaller versions of themselves until they reach something so simple it doesn't need recursion anymore. So yeah, that's about recursion. That's the overview of recursion. So the first topic here is we have recursive methods. So we'll talk about how to write them so they're clear and correct and easy to test. So at a high level, a recursive method has same pieces as any other method, which is name, parameters, return type. But there's the twist. The parameters usually change with each call. That changes how we make progress towards stopping. So again, two questions I want you to ask every time you see recursion. What's the base case, the simple input that returns immediately, and how do the parameters move towards the base case on each call. So those are the two questions that you ask. So then we have return values, which is combining sub results. So most useful recursive methods don't just print something, they return a value built from smaller results. So think divide the work, solve the smaller piece, combine. For example, the sum of first n numbers. So if n is 1 and the answer is 1, that's a valid base case. Otherwise, the sum of first n numbers is n plus sum of the first n minus numbers. So that's recursive case. So the method returns either 1 when n is equal to 1, or n plus let me just write it. It returns 1 when n equals 1, or n plus sum to n minus 1. When n is greater than 1. So each recursion step shrinks the problem by 1 and adds n on the way back up. So if you prefer a different base, like for example n equals 0, 0 also works. So pick one and be consistent in your tests. Let's see a demo with this similar example. Let's say your sum to n. So you'll walk it and let's say n is 3. So sum to 3 calls sum to 1, sum to 2, and plans to add 3 later, and then sum to 2 calls sum to 1 and plans to add 2 later, and then sum to 1 hits the base case and returns 1. So basically the sum to 2 returns 2 plus 1, which is 3, and then sum to 3 returns 3 plus 3, that's 6. Yeah, you'll notice the shape, it go down with smaller inputs and come back up, combining results. So that's this small demo. Next we have tail and non-tail. So a tail recursive method returns directly the result of the recursive call, no extra work after. Our sum2 is non-tail because we do n plus the recursive result after the call. So in some languages tail recursion is optimized. Java doesn't perform tail call optimization, so don't chase tail recursion for performance here. Prioritize clarity. So a few things to avoid is off by one base case. So you're using, decide if you're using n equals 1 and returns 1, or n equals 0 returns 0. So mixing those leads to wrong numbers. For n is equal to 1, if you accept n less than or equal to 0, define exactly what to return. Often it's 0, and document it. So, and recomputing values unnecessarily. So in this problem each step calls once, so it's fine. But in other problems like naive Fibonacci series, you might recompute the same subproblems repeatedly. So if you see multiple recursive calls with overlapping inputs, consider memorization or an iterative solution. And forgetting input validation. So when someone calls sum2 -5, decide your contract, which is the common approach. Treat n less than or equal to 0 as 0, or throw illegal argument exception. Don't leave it undefined. So how to design recursive method is you define the problem in one sentence. Like for example, return the sum of first n integers, and then you pick the base case, like if n less than or equal to 0, return 0, or if n equals 1, return 1. So that's your pick your base case, and then define this smaller subproblem, like sum of the first n is n plus sum of the first n minus 1. So that's that's defining the smaller subproblem. And then you ensure progress. So n decreases by 1 each call, so that's progression. And then decide on input validation. So if n is negative, return 0 or throw an exception. That's input validation. And then last step would be write 3 to 5 tiny tests to lock down behavior. So yeah, that's about so yeah, recursive methods change their parameters each call. This is the progress. They usually return a value that combines a smaller answer with a local step. So be decisive about base case and input contract. Keep it clear first. Optimize only if you prove it's too slow. That's about recursive methods. Next we have binary search. So we're gonna look into binary search, the class of recursive search on sorted data. Emphasize on sorted. If the data isn't sorted, binary search is the wrong tool. The idea here is look at the middle. If the target is smaller, search the left half. If bigger, search the right half. So each step cuts the program in half, which is why the time grows O log n, super fast compared to scanning one by one. So we'll write a method in this shape, binary search, let's say input int a int target, int low, int high. And basically it returns the index if found or -1 if not. So A is your sorted array, and target is what you're looking for, and low, high define the current window you're searching inside. So at the start you'll call with low is equal to 0 and the high is equal to a dot length -1. Every recursive method needs a base case. For binary search, it's if low greater than high, the window is empty, not found. You return -1. So next compute the middle safely. Don't do low plus high divided by 2. That can overflow on very large indexes. So prefer something like mid is equal to low plus high, sorry, high minus low, then divide by 2. So now you compare, you first a mid equals target. Let's say I'm just writing the pseudocode here. Mid equals target, return mid. If target greater than less than mid, you search for search left, binary binary search a comma target comma low comma mid -1. Now if target is greater than a mid, you'll search the right side. Binary search a target mid +1 and then high. So remember, this is a pseudocode. It's not like an actual code. That's the whole recurrence. Look in the middle and cut the problem in half and recurse. Let's take an example. Let's say a equals 2, 4, 6, 8, 10. Your target is 8. So now low is equal to 0, high is equal to 4, because we have the index is 4. Then we calculate the mid here. Your mid is, let me actually, your mid is this equation. We have the low is 0 plus 4 minus 0, and then divided by 2, which gives you 2. Then we search for a mid, which is basically a, mid is 2, so we are searching for a2, which is 6, because this is 0 index 1 and then this is 2, so we got 6. So target is 8. So what would be the next step? Can anyone guess?
Let's compare 6 to 8.
Yeah. You check 8. If 8 is greater than 6, and search for the right half. Then it becomes mid becomes low becomes 3, and high becomes high stays 4. And now the mid will change. So the low is 3, and we added high is 4 minus 3 divided by 2, which gives 3. So A is now A is 3. So mid is 3, which gives us 8. Now you check it with your target. So now 8 is equals to 8. You found the target and then you return 3. So if the target was 5, you'd bounce left and right twice and eventually reach a window where low is less than high, then return -1. No drama, just halves. So why the time O log n? Because every comparison halves the remaining search space. So n is n by 2, n by 4, n by 8, it goes on. So how many times can you half n before you hit 1? So that's about log 2n times. So that's why binary search is go to for big sorted data sets. But yeah, it's a good recursive model. So some of the common things to avoid is use low greater than high to stop when the search window is empty. So using low equals high by itself often misses the last element or loops awkwardly. And mid calculation overflow. Always compute mid as low plus high minus low by 2. It's a tiny change that avoids rare but nasty bugs. So and forgetting the sorted requirement. Binary search only works on sorted arrays or on sorted subrange. So if your data isn't sorted, sort first or use linear search instead. And duplicates. If the array has duplicates, you need the first or last occurrences. The basic binary search isn't enough. You'll tweak the boundaries, but now returning any matching index is fine. Yeah, that's about. So let's go over the last topic for today, which is adding output statements for debugging. So let's talk about one of the simplest and honestly most effective ways to understand recursion, which is trace prints. So when you're writing a recursive method, sometimes you hit that point where you're not sure which call is which. Maybe the numbers aren't matching your mental picture, or you're not confident the base case is ever hit. That's where trace output comes in. So what are trace prints? trace prints are just system.out.println statements that you temporarily add to show when you enter a recursive call and what parameters are, and when you exit the call what value it's returning. So it's the visual uh, breadcrumb trail through the call stack. So let's say you're tracing a simple recursive method like factorial n. So each time the method calls itself, we print something like entering factorial 4 or returning 24 from factorial 4. So those messages show you how recursion dives down to the base case and unwinds back up with results. And indentation, which is here's the part that makes trace prints much easier to read, which is indentation. You can add spaces or tabs depending on the recursion depth. If you pass a depth parameter or calculate it somehow, you can do something like print 2 spaces for each depth level. Depth 0 is your no indentation, depth 1 is 2 spaces, depth 2 is 4 spaces, and so on. So the output might look like with the indentations, like something like enter factorial 3, and then you 1 space or 2 spaces. So yeah, the output would look like something like this. It goes on depending on how you structure your indentation. So now you see the structure of your recursion, the nested calls and how they fold back up. It's like watching the stack frames open and close in the real time. And next we have controlling the noise. So one warning, trace prints get noisy fast. That's why it's smart to use a flag. Sometimes it's like a boolean trace is equal to true, and wrap your prints inside if trace checks. That way when you're done debugging, you can just flip the flag to false instead of deleting all your print statements. It's a clean toggle. You can even control how much detail you print, just parameters and results, or timing information. Timing information if you want to get fancy, and few things to avoid. So too much output. So if you print every micro step, you lose the big picture. Focus on parameters and return values only, and forgetting to remove and disable the prints before turning in or grading. That will clutter your output and confuse others. And then misleading prints. So make sure your print actually shows what's happening. Include both the method name and the current parameter so it's clear which call is printing. So why this matters is recursion can feel mysterious until you see it in action. So when you print both the entry and return values, it suddenly makes sense. You realize that each call has its own copy of variables. Each one pauses waiting for the next one, and then they unwind in reverse order. That builds intuition, not just debugging, but for writing cleaner recursive code later. So that's all for today. We'll discuss the rest of the topics on recursion in the next session.